So I sent out an email a little bit ago, just alerting you to the fact that still haven't finished the exams, partly because of the stupid vaccine. The helpful vaccine. Have you thought about this mRNA technology? It's pretty amazing. And it's been under development for a number of years, 10 to 15 years, but it's been in the lab. And the medical community tends to be very conservative. So they don't like to try new technologies on people until they have some reason to think it's actually going to work and not hurt people. So it turned out the pandemic was the perfect opportunity to test out this mRNA technology. You basically design, in this case, the vaccine. So they get the genetic sequence of the coronavirus in this case, and it's not quite like this, but they type it into their computer and boom, they have the design for the mRNA vaccine. So this was tried twice by two different companies. We give credit to Pfizer. Actually, Pfizer is just the kind of big company that's overseeing the testing and manufacturing distribution. It was actually developed, theirs was developed by a German company, very small biotech company. They don't have any products. They've never sold anything. And then Moderna, which is in a similar situation. They're a little further along as far as the company goes, but same thing. And so this is why the two vaccines are so similar in terms of their effectiveness, even in terms of their side effects, is because they were both designed using the same basic technology. And the numbers are incredible. If you remember early on, a year ago now, they were talking about hoping to have a vaccine in 12 to 18 months, which everyone thought that's not possible. There are still things that we do not have a vaccine for that we've been working on for years and years and years. Most of the existing vaccines have taken many years to develop. Obviously, when you have a global pandemic and people dying left and right, and I don't mean to make light of it at all, that creates a significant sense of urgency to try new technologies and to be more aggressive with the timeline. So the way they did that was they did all the normal phase 1, 2, 3 testing, but they actually started manufacturing millions and millions of doses of these vaccines before we knew they worked. So it was a huge gamble, but again, given the economic consequences of the pandemic and so forth, it made sense and it paid off. So we got a vaccine in less than 12 months, two actually with the mRNA technology, which are very, very effective. I started to say at the beginning, they were saying 12 to 18 months at best, and we hope for like 60, 70% effectiveness. The flu vaccine that we get every year, you know how effective it is? It's like we're happy with 40 to 50%. It's terrible. So when it came in, the mRNAs came in at 94, 5%. It was just, it blew the doors off the whole thing. So, but anyway, the point is that mRNA technology is so amazing that you can actually kind of design treatments for cancers, for obviously viruses. It's really going to be a game changer for us. So I feel privileged to have been able to be part of the grand experiment with this new technology, but right now I'd really just like to be home napping. So I may not be my usual jovial self. We'll see how this goes. All right, so we were talking last time about the numerical solution procedure. It's a 3-step process that takes us from the physical system to an approximate numerical solution. So we start with the physical system. That's the reality. That's the thing we want to model. We want to be able to solve. We want to understand. And the first step is to apply the relevant physical laws and models, approximations, assumptions that will lead from the physical system to a mathematical model. And as I said last time, that's what most of your classes are doing. So you're starting with, if it's fluid mechanics, you say, okay, we've got this fluid system. let's apply the relevant physical laws and make some assumptions, and then we'll end up with the governing equations, Navier-Stokes. And heat transfer, same thing. 202, same thing. So most of those classes is about taking your physical system, your real physical system, and deriving the governing equations for that type of behavior. And whenever you can, getting analytical solutions, which isn't typically very often. So when you can't, then you can proceed with the numerical solution procedure. The second step is to, I will also warn you, I taught this morning and really strange things were coming out of my mouth. So clearly it's affecting my brain function. So just excuse me if I say weird words that just don't make sense in the context. I will plead. I don't know, what am I pleading? Not the fifth, because I'm talking all day long, but yeah, the fifth is like when you say, I don't want to talk about it. So I'm like, it's like the opposite of the fifth. It's like the anti-fifth. It's the integral of the fifth. There you go. Woo, think about that. So forgive me if I say some strange, screwy things. All right, so in any case, we have our mathematical model, our PDEs, ODEs that govern the system. And then we discretize it, and that's where we were last time. We started with the simple spring mass system, and we did this part. We did step one to get the mathematical model. I'll remind you that. And then next we'll do the discretization, which converts that continuous differential equation into a system of algebraic equations. And then we just want to solve those. Big system of linear algebraic equations, solve those using some matrix solver to get the solution. So once again, this part is basically from your other courses. This part we've already addressed in chapter 2. And so our primary focus now in chapter 8 is on the discretization methods kind of sandwiched in there in the middle. So we had our spring mass system with forcing, F cosine omega t forcing. We identified the physical laws, in this case, Newton's second law, and that, use your words, Castle, that enforces conservation of momentum. And so that's a physical law that must be satisfied. And then we made some additional assumptions. We said, okay, let's neglect the mass of the spring. Let's assume that the spring is linear and elastic, make our lives easier. And the drag we're going to take into account as the mass moves up and down. But we're going to just assume it's a low speed drag, which has a particular, it's called Stokes drag, and it has a particular form of the drag. So we put all those in. We used F equals ma. And we got this system of, well, it's not a system, it's one single equation. And that's where we ended up last time. So this is a second order, because the highest order derivative is 2. It is linear, because I only have u's. I don't have any u squareds. I don't have any sines of u's. I don't have du, dt's times u's. I don't have anything with u's and u's. So it's a linear, second order, non-homogeneous ordinary differential equation. The non-homogeneity comes from the fact we have a non-zero right-hand side. We have this forcing term on the right. On the right, you see all the stuff that doesn't have u's in it. All right, it's what we call an initial value problem, or IVP for short. We start at t is equal to 0. What is the initial state of the spring mass system? And then we let it go. And we calculate the solution of 8.2 as a function of time. And then that will give us the solution. So we need 2 initial conditions because it's second order. So we have an initial condition on the position at t is equal to 0, that'll be u0, and an initial condition on the velocity at t is equal to 0, call that v0. So this is our mathematical model. We have the equation, and we have the initial conditions. That is step 1, and that gives us our mathematical model. Now it turns out, because this is a second order linear ODE, we can solve it exactly, but we'll pretend that we can't. And we'll continue with the numerical solution procedure in order to see how that all pans out. So the second stage, the second step, is to discretize the problem. We're going to discretize both the domain and the equation itself. So we're going to take the continuous time domain. T starts at 0 and goes for all time, and it's continuous. Continuous means we have an infinity of times. At every single time, between 0 and infinity, we want to know the solution. So we're going to approximate the continuous time domain using discrete locations in time. So what that's going to look like is we have our time coordinate, t is equal to 0, that's the initial conditions, and then we'll have increments in time. So this might be I, this would be I plus 1, and there's a distance delta t, the time step between them. So we're going to march from t is equal to 0, where we know the initial conditions, and rather than continuously solve for all time, which is what you get if you get the exact solution, we talk in terms of marching. So we're going to take a step to the first time step, calculate the solution there. Second time step, calculate the solution there. Once you get it at a generic I, you go ahead to delta t, get it at I plus 1, and you just keep continuing marching in that fashion. So that's how we discretize the domain itself. We take time steps, delta t's, such that the ti plus 1 is ti plus delta t. So ti plus 1, which is this value of time, plus the delta t is this value of time, exactly like you would expect. Now, if you remember way back when we did Couette flow, way back in chapter 2, I think, and we were looking at various applications to try to motivate why we might want to solve systems of linear algebraic equations, one of the examples, one of the applications I showed you was a Couette flow fluid dynamics example. And I motivated the way that we will discretize the differential equation using the definition of the derivative. So let me remind you, this is exactly what we did back in the beginning, back in chapter 2. Let me remind you what we did. So du dt, that's just u prime of t, it's an ordinary derivative. And by definition, the derivative is the limit as delta t goes to 0 of u at t plus delta t minus u of t over delta t. That is simply the rise over the run. It's the slope, right? Derivative is the slope. So this is the rise, how much u changes from one time to the next, divided by the run, which is the delta t, rise over run. And the way we're going to approximate this then is rather than taking the limit as delta t goes all the way to 0 to make it an exact derivative, we're going to approximate it using a small but finite time step. So this is the final result, but it's only an approximation for that derivative u at t plus delta t, where delta t is small, minus u at t over the small delta t. And that'll give us an approximation for that first derivative. So that's motivating it from the definition of the derivative. We'll more formally do this using Taylor series in a moment, but for now, this is a good starting point. And it gives us kind of an intuitive feel for what's going on here. Now, they're called finite differences. It's a finite difference method because you can see we have a difference, subtraction, over a finite distance, delta t distance. So that's why it's called finite difference methods. And so the value of the position then is calculated at successive time steps in turn. Like I said, we're going to kind of march forward in time, get the solution at the first time step, then the second time step, third time step, and move on and on and on. So in the end, that's step 2 in the numerical solution procedure. In the end, we get a system of algebraic equations to solve for those solutions. And then step 3, of course, is to solve them. We'll kind of sweep that under the rug because we've already addressed that in chapter 2 using matrix solvers, whatever makes sense for the particular system of equations we have. And that gives us our numerical solution. So this is for G on the Earth, mass of 1, K constant, spring constant 1. The C, that's the damping, is 0.01. Force of the forcing, the magnitude of the forcing is 1. Frequency of forcing is 0.2. And if you put that in and you solve it forward in time, you get this sort of oscillatory behavior as you would expect. Now this is, this is up and down. Now, not left and right, but up and down. So it actually looks correct. So it goes down, pulls up, down, over and over again. Okay, so that's this 3-step process for a simple ODE. Let's think about how we determine whether these solutions are correct or not. There's 2 aspects when it comes to checking on the solutions and how accurate they might be. One is called, these are the two V's, validation and verification. And sometimes it's hard to remember which one is which because they're both kind of similar words, validation, verification. So I'll give you some questions that we're asking that help us to determine whether it's validated and verified. You actually need to think about this in terms of doing both. So basically at each stage of the numerical solution procedure, so 1, 2, 3, you're introducing errors. So step 1, when you get the governing equation, you're introducing modeling errors because your model is not correct. It has some assumptions in it. It has some approximations in it. So it's likely not correct. So you have modeling errors. Your governing equations are not quite correct. Then step 2, the discretization step, which is the one we just talked about, at least in a simplistic fashion, that also introduces an error, discretization error, which we'll talk more about. And then in the third step, you get numerical errors. So you're solving the system of equations, and usually you're using iterative methods to do that. And so because you're iterating, you get convergence errors, iterative convergence errors that we talked about in chapter 2. So think in terms of doing something like Gauss elimination, Jacobi, SOR. So we have those numerical errors that arise from step 3. So step 1 is validation. So validation, you're looking for quantification of the modeling errors, that's step 1, in the computational model. So the kinds of questions that you're asking are, am I solving the correct equations? So did I do a good job in step 1 of deriving the governing equations? Are they correct? Am I capturing the physics correctly? Which is another way of asking the same question. So we start with reality. We get the governing equations. Do those governing equations indeed make sense in terms of modeling that real physical system? So that's validation. Is the solution qualitatively correct? So when I put the block on the incline, does it go down like I expect? Qualitatively is not numbers. Qualitatively is behavior. Is the behavior of the solution, does it make sense? Is it correct? So validation is accomplished by comparing your numerical results or your exact solutions of the mathematical model with highly accurate experiments. So you have a mathematical model of the system. The only alternative to check it against is experimental results for that system, the real system. And so that's how you validate. Sometimes that's straightforward, lots of experimental results, but sometimes that's not so straightforward because you don't have them. The second V is verification. So this is a quantification of the discretization and numerical convergence errors in the computational model and its solutions. So in other words, this is steps 2 and 3. Validation is how good a job did you do on step 1. Verification is how good a job did you do on steps 2 and 3. So now the parallel questions are, am I solving the equations correctly? So the first one was, am I solving the correct equations? Now the question is, am I solving those equations correctly? That's steps 2 and 3. Am I capturing the mathematics correctly? So the mathematical model is obviously math, it's a differential equation. Does that capture the mathematics correctly? Does my solution capture that correctly? Is the solution quantitatively correct? So now are the numbers right? So do I have an exact solution? If so, I can compare my numerical solution to that. Or another form of verification is to use what are called benchmark solutions. So there's a lot of discussion about this in the computational community and fluid mechanics, heat transfer, solid mechanics, and so forth, is benchmark solutions. So these are problems that people have been solving for many years. They may be problems that people care about physically, they have certain applications that are interesting in their own right, or they might just be problems that we have numerical solutions for, regardless of whether the applications are there. And they provide a benchmark against which to compare our numerical solutions. So you're either using highly accurate numerical solutions from other codes, from other settings, and comparing yours with those because you trust those, or like I said, you're using exact solutions possibly if they're available. Usually you don't have an exact solution for the actual problem you want to solve. If you did, you wouldn't be doing it numerically, but you might have an exact solution for a simplified version of it. So there might be a simplified version of the system that you can get the exact solution for, and therefore use it to verify that solution. And then you have confidence that it's doing the right thing, and then you can go and solve the actual problem that you want to look at. Now, everything we do in this class, and many of your other courses as well, is to focus in on one of those three steps. So as I've said many times now, step one, that's most of your what we call engineering science classes. Your 200 and 300 level engineering science classes. And then your math classes, of course, are looking at differential equations, calculus, and linear algebra of these things, the matrix methods, and so forth. So pretty much everything you're doing in some way has an impact on this numerical solution procedure. So like I said, I think it's a helpful framework to think about. If you ever feel like I'm kind of lost, not really sure what we're doing, just stop and think, are we doing step 1, 2, or 3 in the numerical solution procedure? All right, there's various approaches in carrying out step 2. So the two that I'll mention are finite difference methods and finite element methods. There are others, but these are by far the most common in general purpose contexts. So we'll discuss both of these. We'll primarily focus on finite difference methods, and that's because they're in widespread use, they're very flexible, and they are really very straightforward to understand. It's purely based on Taylor series expansions, which of course you've all hoped you'd never see again, but I'm going to dredge them up. If you want to learn more about finite element methods, then you can take, there's an elective course, MMAE 451, that covers FEM. So I'm going to just, discuss both of them, kind of summarize one slide, both of them pros and cons, and you'll get a sense for why we have these two and why they're so useful. So first, finite difference methods, and again, this will be our focus in this class. So basic approach. The starting point is the ODE or PDE. So that's your governing equation from step 1. That's the starting point. And then we're going to use Taylor series-based finite difference approximations. I kind of motivated them using the definition of the derivative, but we'll more formally derive them using Taylor series. And so we're going to apply those to the standard differential equations. The product of those, the outcome of those, is going to be a system of linear algebraic equations that we need to solve. That's step 2. Step 2 of the discretization method. And it's a local approximation method because, as you'll see, you're going to look at the point itself, I, and then points to the right, points to the left of that point. So it's a local approximation as opposed to being global. It's very popular in research settings for reasons that we'll discuss in the advantages. Not so popular in commercial codes and in industry for reasons that we'll discuss in the disadvantages. So in terms of advantages, it's very straightforward, which is why we're going to focus on that here. It's very straightforward to understand, very straightforward to implement. It's just Taylor series. I know you've forgotten Taylor series. I'll remind you how Taylor series work. They're actually pretty amazing. And we use just standard, what are called structured grids. A structured grid is just what it sounds like. It's highly structured. So the grid will look something like that. So we can identify a given cell or point in our grid simply by looking at the X and Y locations, and then they're all ordered X and Y. So the very simple, very structured grid. You'll see that as we go through this. All right, so that's great. It utilizes the familiar form. So in almost all cases, when you derive these governing equations, they're almost always being derived in differential form as opposed to an integral form. And they're very general. So we can apply them to a wide variety of problems, whether in fluid mechanics, heat transfer, solid mechanics, electromagnetics, on and on and on. All areas of engineering, all areas of science, physics, and so forth, you can apply these finite difference methods. And by extension, you can perform complex physics. Complex physics means there's multiple types of physics or forms of physics involved in the problem. So in aerospace applications, you design the structure of the plane. The plane has to fly through the air and have lift and drag. So that's the aerodynamics of it. And then you have to worry about, things called flutter. So that's fluid structure interaction. And then there's heat transfer in the engines, the combustors, and so on. There's reacting flows. So that's all multi-physics. There's a lot of physics involved. And the nice thing about finite difference methods is it's relatively straightforward to incorporate that complex physics. Typically, when you do step 2 and you get the linear system of algebraic equations, typically those equations are sparse and highly structured matrices. By sparse, we mean there's lots of zeros. So sparse matrices just mean they're generally big, and a lot of the elements are 0. Highly structured means, if you remember, we talked about tridiagonal systems, banded systems, there are block tridiagonal systems, but they have some sort of structure to them. So they're sparse, lots of zeros, and the non-zero elements have some sort of structure. And what that means is, when you're performing step 3 in the numerical solution procedure, you can take advantage of that sparse structured nature of the system. You don't have to do kind of a brute force process like LU decomposition or Gaussian elimination. You can have kind of more of a targeted strike in order to solve them. Disadvantages, I'm only going to list one, but it's huge. And that is, it's extremely difficult to implement for complex geometries. I said more difficult, it's actually very hard. It's not impossible, but it's hard. So if you have complicated domains, shapes, finite difference methods are probably not your best option. And that, of course, is very important in industrial applications. And that's why finite difference methods are often not used in commercial codes, open source codes that are used in industry. The main alternative, not the only, but the main alternative in general is finite element methods. And you may have heard of these. The basic approach is to start with the variational or integral form of the equations as opposed to the differential form. It's the same physics, it's mathematically equivalent, but it's just put in a different form. Now that's not the typical form that you're used to seeing these equations in, but that's just an extra step. So you're applying the conservation equations in an integral form. And you're applying them over finite elements rather than finite differences. You're going to break up the domain into tiny little elements, finite sized but small elements. And then you're going to solve for the dependent variables on those little elements. It produces a set of algebraic equations, but they could be linear or nonlinear. So finite difference methods always produce linear systems of algebraic equations. Finite element methods may produce linear, but they also may produce nonlinear algebraic equations. Now we know how to solve that. We talked about Newton's method and so forth for systems of nonlinear equations. So we can do it, but it is more computationally intensive. It's still a local approximation method because we're looking at these little finite elements. So each finite element just needs to know what's going on in the neighboring elements, north, south, east, and west. How you doing up there? How you doing over there? And then it can determine the local solution based on that. So both of these are local approximation methods. It's very popular in commercial codes. Generally speaking, any code that had its origins in solid mechanics or conduction, so conductive heat transfer, they're almost all based on finite element methods. In fact, for years, it was thought that finite element methods could not be applied to things like fluid mechanics where you have nonlinear PDEs. Eventually, they determined how to get around that problem, which we won't talk about, but so that's no longer a barrier. So a lot of the codes that are based on finite element methods have their origins in solid mechanics and or conductive heat transfer. So what that means is for fluid mechanics, old codes would be based on finite difference methods, or another method, which we're not going to talk about because it's only used in fluids and heat transfer, and that's finite volume methods. Advantages, there's only one listed here, but it's a huge one. And it contrasts with the disadvantage. It's perfectly, meshed with the disadvantage of finite difference methods. It's very natural, actually, to treat complex geometries. The grids are inherently unstructured. So even if you could use a structured grid, when you use a finite element method, it's going to be unstructured. So there's no problem with doing complicated geometries. An unstructured grid is, if it's 2D, it might be triangles, for example, and you can piece these triangles together however you want. You can make some bigger, some smaller, and you can piece them together in a way that produces any shape you want. But they're unstructured. So you've lost the just tell me the index in the X direction, index in the Y direction, to tell me which one I'm looking at. And then the ones to the left and the right, well, they're not just I plus 1 and I minus 1. They're whatever. So that leads to one of the disadvantages, and that is your unstructured grids significantly increase the computational complexity as compared to structured grids. So not only are they conceptually more difficult to think about and picture and so forth, but they're also more difficult to code because you have to have a way to kind of map these elements to something that makes sense in an overall global sense. So the fundamentally unstructured grid aspect is both its main primary advantage, because we can do complex geometries, but it also is what makes it more difficult from an accounting point of view. These solution methods are comparatively inefficient. Oftentimes, most of the time, your system of equations are dense, kind of like me, dense as opposed to sparse, so lots of non-zero values, and they're often unstructured matrices as opposed to structured matrices. So, all right, and as I said before, they may lead to nonlinear systems of algebraic equations. So what that means is, of course, you're going to solve this on a computer anyway, so the computer is doing all the nasty calculations. But what you'll find is if you see a calculation being done on some cool system, it looks really cool and blah, 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 and you look into the numerics and you find out, oh, okay, it's done with the finite difference method. It would not be unusual today for them to tell you, if you ask them, how many grid points did you use? How many, what was the resolution and so on? It would not be at all unusual for them to say, I've used millions, or sometimes now even tens of millions of grid points. Whereas if you see a finite element calculation for the same problem, it's more likely that they're using tens, maybe hundreds of thousands of finite elements. And that's simply because the computational task of solving the systems of equations that result is much more time consuming on the computer, because they may be nonlinear and because of the reasons that I stated here. They're dense and unstructured. So there's trade-offs in all respects. And I'm not, I mean, some people think, oh, well, finite element methods, eventually they'll kind of catch up and overtake finite difference methods. I don't think that's ever going to happen. There's pros and cons to both. They're highly complementary. The advantages of one are the disadvantages of the other, and vice versa. So I would expect that, at least for my lifetime, both will be extremely popular in a broad numerical methods sort of context. All right, any questions about those finite difference, finite element methods? All right. So let's talk about the formal basis for finite differences. This is going to be the hardest topic for the rest of the semester. Okay, just warning you. Why? Because it's lots of Taylor series. Taylor series, you thought you would see them for the last time in Calc 1. And you thought at the time, they're just trying to impress us. Those math professors, they're just trying to impress us. I don't understand why, how these could be used. I don't understand in what practical way they might be a benefit in my life. Well, here they come. All right, so you haven't seen much Taylor series for the last couple of years. Here they come. So I'm going to remind you about Taylor series. They're not that difficult actually, and we'll show how we can use them to approximate the derivatives in our differential equations. Okay, so let's kind of remind ourselves of the definition of the derivative. This is what we just had a moment ago. Same thing. U prime is du dx, and it's this limit as delta x goes to 0 of u of xi plus delta x minus u of xi over delta x. Rise over run. Great. If you then take, rather than delta x going to 0, if you say, okay, well, let's keep delta x small but finite, then it becomes an approximation to the first derivative. And it looks like this. No limit, delta x is small. Or we're going to use the shorthand. So ui equals u at xi. So that's just a shorthand. That's just abbreviation. When we say u subscript I, what we really mean is u at x sub I. Same thing with u at I plus 1, u sub I plus 1. That means u at xi plus delta x, or at xi plus 1. Okay, so that's the shorthand that we're going to use. This is what we call a forward difference, because I'm looking at the point itself, I, and the point to its right, forward. So that's a forward difference. Now, again, that's very unsatisfying because we just kind of made it up. It turns out to be correct, but we're going to derive it formally using Taylor series. Okay, let's think about, could we get something better? This is what I call the forward difference. It's ui plus 1 minus ui over delta x. So that's rise over run. And you might think, well, we can probably do better than that, right? What if we did u of xi plus delta x, like before, but now minus uxi minus delta x? Why might that be better? Well, let's kind of look at this intuitively. So let's say we have some function. This is our u. And let's look at 3 points. So this is xi, xi plus 1, and xi minus 1. And these are a delta x apart. Okay, so uniform grid. Now what we want is, if we want the first derivative, du dx, at x sub I, so we want this slope. So that would be the exact value of our derivative. It would be the slope of the function u at that point. That's what we want. Now, of course, we don't have that. We're going to approximate it. The forward difference is this. That's the forward difference. So it's ui plus 1, that's this point, minus ui divided by the distance between them, delta x. So that is an estimate for this slope. You can see it's not a very good one. I could do the same thing, but backward. I could do this. That would be a backward difference, just like the forward is a forward difference. That doesn't look very good. What about this one? Okay, that is called a central difference. And you look at those 3 possibilities, just imagining them intuitively, and you say, which one is closest to being the exact? Well, clearly the central, which would, I think, rise over run be ui plus 1 minus ui minus 1 divided by the distance between them, which is 2 delta x. And in fact, that's correct. But again, we'll derive it formally. Don't take my word for it. No reason to trust me, especially the day after you get a vaccine. So that will be correct. Rise, the difference between these two, overrun the distance between them. All right. So I think intuitively that this, which is a central difference, ui plus 1 minus ui minus 1 over 2 delta x, I think intuitively that that should be better than our forward difference or the imagined similar backward difference. In fact, that is the case, but how do I know that? How do I convince myself that that is true? All right, so that brings up the obvious question: how can I derive these in a formal manner? How can I get these finite difference formula in a formal manner? And how can we quantify the error rather than just saying, what is it, TLAR? That looks about right, right? So rather than just saying, yeah, central difference TLAR, it looks better. So rather than just thinking qualitatively, can we quantify how much better, in this case, the central difference is as compared to a forward or backward difference? Did we talk about the European Super League? Do you guys care about this? I won't talk about it if you don't care. Yes, I care. So this is very, very fascinating. So there's been rumors about this for several years that the big European clubs, so this is the Manchester Uniteds, the Liverpools, the Chelseas, Arsenals, this is Barcelona, Real Madrid, Juventus in Italy, and so forth, Inter Milan, AC Milan. So there's been rumors that the big clubs weren't happy with the Champions League, which is the current European competition, which is amazing. I love Champions League. And so they basically, their problem with it is our big teams don't get to participate as often as we deserve, because we're big teams. We should be there every year, whether you think we should be there or not. So normally it's the top teams in various countries. In England, it's the top 4 teams get to participate in Champions League. But in England now, we used to talk about the big 4, which was Manchester United, Liverpool, Arsenal, and Chelsea. Now, because of all the money that's been thrown into these teams, it's actually the big 6, they call it, which is those 4 plus Tottenham and Manchester City. Now, Tottenham is a funny one because they never actually win anything. So they want to be big, but they never actually win anything. Manchester City does, just because, again, they've thrown tons of money at it. Anyway, so all these clubs are complaining because we should be in Champions League every year. The world would be a better place if we were in Champions League every year. So they came out with this rumor on Sunday, and they announced it on Monday that they're forming this Super League, European Super League. And basically it was going to compete with, in their minds, replace the European Champions League, which has been around for many decades. There was an immediate and extremely strong reaction, negative reaction from everybody. Fans, completely against it. Even fans of the teams that were going to be in it, which is all the ones I mentioned. And even the managers of the clubs, the coaches, were against it. They didn't even know anything about it, supposedly. The players were against it. Even the politicians were coming out against it. This is a horrible thing. What's interesting is if you read the British literature on this, it gives you kind of a very different story from the American reporting on this. The American reporting basically is making the argument that this was an attempt to Americanize European soccer or football. So a lot of these big clubs are owned by rich Americans. The family that owns the Tampa Bay Buccaneers in the NFL, they actually own Liverpool. They own Manchester United. Liverpool is owned by the Fenway Sports Group, which is the same people that own the Red Sox, MLB. And so their idea was, well, let's run this like the NFL and the NBA, where we make all kinds of money every year, regardless of how good or bad our teams are. They thought that was a great thing. The reaction was just merciless. They got raked over the coals. All of the domestic leagues said, fine, you want to do that? We're kicking you out of our domestic leagues. So could you imagine English Premier League without Manchester United, the big 6? None of them. They're all gone. They said, okay, UEFA said, okay, fine. You want to do that? We're not going to allow your players on these teams to participate in international events like the World Cup. Kind of a big deal. Within 48 hours, the whole thing came crumbling down in a heap of hubris. It was unbelievable. I've never seen anything like it. They got excoriated. a lot of these owners, these rich owners, which never talk to the press because they don't want to, because most of the fans don't like them. They never talk to the press. They had to come out and make these conciliatory statements. Oh, we're so sorry. And we didn't really realize how important this was to the fans, and relegation promotion processes and getting into these tournaments based on merit. Oh, heaven forbid, instead of just because we're a big team that spends lots of money. It is such a weird concept. It truly is. And it is indeed trash. And thankfully, like I said, it got thrown on the hubris trash heap very quick and amazing in record time. It's just unbelievable. So the interesting thing will be, how much damage has this done to the fans? It's probably a good thing that most of these stadiums are empty right now and the fans are not physically there, because they would not be happy. The songs they would be singing would be unrepeatable. I have no doubt. All right. That's what we're missing in American sports. Fans singing songs. I love it. It's just so awesome. Singing songs at sporting events. We need more of that. So rich American owners, if you want to bring something from the other way, bring over fans singing. You go to a Chicago Fire game. It's like a concert. You've got people banging on drums and playing horns and singing songs. It's awesome. Okay. Now, sometimes you don't want to know what they're singing, because it can be quite inappropriate at times, but it's certainly very entertaining. All right, where were we before I really interrupted myself with the ESL, which is on the hubris trash heap? All right. So yeah. Said all that. Good. Let's do it. All right. So we're going to formalize this using truncated Taylor series expansions. Let me remind you what Taylor series are. They're not that difficult. Let me try to kind of reframe Taylor series and show you how actually quite impressive they are. And then we'll show how we can use them to get these approximations, the ones we've already seen, and others. And in doing so, we'll determine how accurate they are relative to each other. Okay. The whole idea behind a Taylor series expansion is that it allows you to express a quantity locally around in the vicinity of some point. That's the whole point of a Taylor series. So I have information about the function at some point, and I want to know, how does it behave in points close to that point? Whenever you're asking that question, whenever that's the question, the answer is write a Taylor series. I do have a Premier League team. So, and this is actually interesting. I've never had this thought before until this weekend. So I'm a Manchester United fan about, what is this, 2021? So I spent a sabbatical in Manchester, University of Manchester, in 2006, 7, and 8. And so that was really my first introduction to the Premier League and international soccer. Fell in love with Manchester United. Of course, they won like every other year at that time, and so it was great. You know, Wayne Rooney, Cristiano Ronaldo, just amazing, amazing players. So that's my team. But for the first time ever, this past weekend, I did think, I don't know, maybe, I'm not sure, depends how they handle this, I may have to revoke my fandom of Manchester United because of this hubris. Hubris is a great word, by the way. Look it up. There's no better word to describe this whole thing. So it really just shows you how completely out of touch these owners are from reality. They have no clue what's going on at their clubs, which does not give you confidence in terms of the decisions they're making. So go United. The knock on United through the Sir Alex Ferguson era was, and maybe this is part of their motivation for doing this, one of being the Super League, was they won the Premier League like every other year. He was manager for 27. During that 27 years, they won like 13 years, so literally almost every other year on average. But they only won the Champions League, the European Champions League, 3 times. And so that was, so yeah, anyway, that's my team. The Reds, the Red Devils. There's nothing like European soccer. It's a completely different experience. So here, if you go to a White Sox game or a Bears game, Bulls game, you can go in any gate to get into the stadium or arena. You can walk around the concourses, and your seat can be anywhere. So you have the home fans, you have the away fans, but they're all mixed together. You see them at all these games. In Europe, they can't do that. You know why? Because they beat each other up. So you have to separate the home fans from the away fans. So they have a separate section. You can always tell, because if you're watching on TV, you can see a line of green or orange vests. And that's all the security people that are lined up in the stands between the home and the away fans. When you go in the gate for your section, no concourses to walk around. You go in your gate and you go straight up to your seat. No mixing of fans. Everything is completely different. There's all kinds of, it's unbelievable. It's actually quite sad because there is a lot of violence in European soccer. For some of it, well, if you guys into 30 for 30s, some of these are amazing. There's a 30 for 30 on the Hillsborough disaster. If you ever want to be horrified by what can happen at a sporting event, watch the 30 for 30 on the Hillsborough disaster. And I won't say any more than that. It's crazy, crazy stuff. Glory, glory, Man United. Sorry, you made me do it, Tim. Yep. All right, singing at sporting events. Oh yeah, Taylor series. This is awesome. So watch this. So I have my function u of x, fine. And what I want to do is I want to express that function near a point, xi. So xi is a specific point in the domain, specific value of x. And I want to write the function u of x in terms of function and derivative evaluations of that at that point, in terms of the distance from that point. So all these x minus xi's, x minus xi's, x minus xi's, x minus xi's, that's how far away my x value is from my reference point xi. So if I know the distance between the 2 points, and I know the value of u, first derivative, second derivative, third derivative, fourth derivative, all derivatives, guess what? This is amazing. You know all there is to know about that function, absolutely everywhere. So think about this. You have a u of x function from minus infinity to infinity. All you have to tell me is, at a given point, x, what is the value of u of x? What is the value of the first derivative, second derivative, third derivative, all derivatives? And I can tell you what's going on everywhere else from minus infinity to infinity in that function. If you keep all infinity of the terms, which we're not going to do, we're going to truncate. That's amazing. It seems counterintuitive. Do they explain it that way to you in your Calc 1 class? I hope so. Probably not. All right. So that's the Taylor series. That's the general Taylor series. Now let me show you how we're going to use this to get our finite difference approximations. Here we go. So we're just going to start writing Taylor series at different points. So I'm going to write it at x sub I plus 1. Why not? See what happens. Then we'll write it at xi minus 1. I don't know why. Just see what happens. And then we're going to write it at xi plus 2. And we'll just see what happens. We're going to start writing Taylor series at various points and see what we can do. Now, so I'm going to write the Taylor series at x is equal to xi plus 1 about u of xi. Again, abbreviated as u sub I. U sub I is u evaluated x sub I. So the function value, first derivative, second derivative, third derivative, all evaluated at that point, that x sub I point. Then a delta x away, I want to know what the value of u is. So u at xi plus 1, or for short, u sub I plus 1, I can now write as this Taylor series expansion. So that's all that is writing 8.4, where x is equal to xi plus 1, just applying it at a specific point. Great. Well, that was fun. Well, what happens if I solve for the first derivative, du dx? So let's see what I get. Du dx at x sub I is ui plus 1 minus ui divided by delta x. Ui plus 1 minus ui divided by delta x. Does that look familiar? That's the forward difference. Oh. Now, if I keep all of the rest of these terms, then it's an exact representation of the first derivative. But what we're going to do, just to give you a heads up, is we're only going to keep the first term and we're going to truncate all the rest. So it's a truncated Taylor series. And then that will become our approximation for the first derivative. Oh, and that again, that's the forward difference. Okay, that was fun. Let's apply it at x is equal to xi minus 1. So around the same point, u of xi, but now it's u at xi minus 1. So now the delta x is actually minus delta x because we're going to the left. So it's minus delta x squared, which of course is plus delta x squared, minus delta x cubed, which is minus delta x cubed, and so forth. Now let's do the same thing, see what we get. So let's solve for du dx at x sub I. So this is another approximation for exactly the same thing. This one was a forward difference, dun 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 dun. This one is a backward difference, ui minus 1 over delta x. Same thing. If I get rid of these terms, if I truncate all of these terms, I now have a finite difference approximation for the first derivative of u with respect to x. Well, that was fun. What about the central difference? Well, what if I take the Taylor series for xi minus 1 and the Taylor series for xi plus 1, and let's subtract them? I don't know why, it just seems like a fun thing to do. So take these two, this one and this one, and I'm just going to subtract them and see what we get. So you do that, and you end up with this. I again solve for du dx, and I get this. So again, this is an approximation for the same thing, du dx at x sub I. I have 3 different approximations for exactly the same thing, the first derivative at x sub I. And notice what it is, ui plus 1 minus ui minus 1 over 2 delta x. Oh, well, that sounds familiar. That's the central difference. We just formally derived the central difference. So we just derived the forward difference, backward difference, and central difference approximations. If you look at each of those 3 side by side, you can see ui plus 1 minus ui over delta x, ui minus 1 over delta x, and ui plus 1 minus ui minus 1 over 2 delta x. Again, rise, overrun, rise, overrun, rise, overrun. Now I've added this extra bit over here. The way this is read is literally order of. So this one is order of delta x. This one is order of delta x. This is order of delta x squared. Now, where do those come from? Let's talk about where they come from first. So if I go back to my backward difference, which is this one, look at the next term. It has a delta x in it times the derivative. The next term would have a delta x squared times the third derivative, and so on. So each term in the series is getting smaller and smaller and smaller because delta x is small. So when I square a small number, it's smaller than delta x. If I cube that small number, it's smaller than delta x squared, and so forth. So each of these terms is smaller than the preceding term. So the truncation error, the error because we're truncating this Taylor series approximation, comes from the first term, the biggest term that we're not including, and that is order delta x. The 1/2 times the derivative, that's order 1. That's an order 1 number. And so the order of this term is delta x, which is small. The next term is delta x squared, so that's even smaller. So that's the idea. The backward difference is the same thing. The first term that we're truncating is order delta x. In the central difference, the first term that we're truncating, oh, I see now, it's order delta x squared. So that's why this is first order, delta x, first order, delta x. This is second order, delta x squared. So again, delta x is small, so delta x squared is even smaller. So the error, the truncation error that we get doing this because we've done this truncation is smaller, order delta x squared, for the central difference as compared to the forward and backward difference. That's what we thought, that's what we expected intuitively, and indeed that is formally the case from the Taylor series. Well, this is a lot of fun and you're going to want to do more, so we'll do more in a second, but let's make a few comments. So they keep saying this is the truncation error, order delta x squared. You don't actually use these in the approximation, as you'll see. They're just there to show you how good or bad they are. What is the order of the approximation? And again, the second point is what I just said. This is the largest of the terms that we're neglecting. That is the truncation error. And so again, I just used these terms a moment ago. We say if it's order delta x, we say it's first order accurate. That's delta x to the 1. If it's delta x squared, we say it's second order accurate. If it was delta x cubed, we say it's third order accurate. That's just the terminology that we use to describe those truncation errors. Ooh, somebody has something intelligent to say. Or it could be snarky. Have you seen the movie Green Street Hooligans about the fighting? Oh, it's unbelievable. And it's actually quite, so we think Chicago Bears and Green Bay Packers fans don't like each other. It's nothing like these European clubs. Not so much in England anymore, but in some of the other countries, it's, so they don't have guns like we do because we're idiots. But yeah, they show up to games with knives. They start stabbing the fans from the other team. Seems like a fun thing to do. Of course, alcohol, I'm sure, is never involved in these sorts of things. But yeah, so they call them hooligans. That's kind of a polite term to reference the behavior that they often exhibit. In some countries, they actually, not in England, interestingly, but in some of the other countries, Germany has this. I can't remember, the Spanish clubs don't, but in some countries, they actually have big metal fences up around the field, around the pitch. And that's to keep the fans away from the players because we have to worry about that sort of thing. Here in this country, we let the fans run onto the field, sometimes with no clothes on, in order to get their 15 seconds of fame. And it's always embarrassing when they get tackled. It happened during the Super Bowl. I forget what the guy was advertising, but it was pretty embarrassing for everyone involved. Anyway, where was I? Okay, said this. So again, truncation error tells you how good the finite difference approximation is. It comes from the Taylor series and it gives you the order of. It doesn't tell you the actual number. Order of means it's of the order of delta x. If delta x is 0.01, well, it's not 0.01, but it's of that order. It's some constant times 0.01. If it's order delta x squared and delta x is 0.01, then it's 0.001, right? So that tells you the rough magnitude of the truncation error. There's also round off error, which we talked about earlier in the semester. And that simply arises because of how numbers are stored on computers and how calculations are done on digital computers. So 2/3 is not 2/3 on a computer, right? So there are round off errors. Those are two separate sources of errors. There's the truncation error, which comes from the discretization method, so that's discretization error from step 2. And then there's round off error, and that comes from how you actually do the calculations on the computer. So even if you had a so-called perfect computer, so all the arithmetic was exact. So if it was exact, you would not have round off errors, but you would still have truncation errors. So step 2 would still result in errors. Okay, like I said, that was a lot of fun, and I know you want to do more. So let's think about how could we get a second order accurate forward difference approximation to the first derivative. And you think, wait, that sounds familiar. No, before we got a first order accurate forward difference approximation to the first derivative. So now we're going to get a second order accurate How do we do that? We just manipulate the Taylor series. So let's apply our Taylor series at xi plus 2. We have xi minus 1, xi, which is the point itself. We have xi plus 1. And let's just for fun, try xi plus 2. Why not? Seems like a reasonable thing to do. So ui plus 2 is ui. Now the delta x is 2 delta x's, because it's 2 delta x's away. The xi minus xi, the x minus xi, excuse me, is now 2 delta x. So 2 delta x squared, 2 delta x cubed, and so forth. Now, if I want to get a second order accurate forward difference approximation to the first derivative, I want to be able to solve for this first derivative, but I need to eliminate this term. And I know that's not obvious at the outset, but if I want a second order accurate approximation, then I need a delta x cubed term. So when I divide through by delta x, it'll give me a delta x squared. So this is, in other words, you can think of it this way. This is the term that gave us the order delta x approximation, because you take delta x squared, divide by delta x, you have delta x. So in order to make a third order accurate, I need to get rid of this term. So you look at your Taylor series and you ask yourself, can I multiply one of them times something and subtract another one? And you say, well, sure, I could take 4 times 8.5 and subtract 8.11, which is this one. Go back and look at it. It's just simple algebra. And you'll find that that gives you this. 4 times this one, which is the Taylor series at ui plus 1, minus the Taylor series at xi plus 2. And that gives you this. You solve for du dx, the first derivative again, and you get this. Oh, well, that's interesting. It's totally different. So this is, again, first derivative. So this is now a fourth approximation to the first derivative. You say, why do we need so many? Isn't one enough? Yeah, not really. Kind of. Depends. All right, so for first derivative, minus 3ui plus 4ui plus 1 minus ui plus 2 over 2 delta x. The first thing you'll notice is it requires 3 points rather than 2. So to have a higher order approximation, you always need to include more points in your Taylor series and therefore in your finite difference approximation. That's always true. So you'll always see that. The next term, the first one that's truncated, was the delta x cubed, which was divided by delta x that gave us the delta x squared. So this is order delta x squared. So this is indeed a second order accurate because of this, forward difference approximation because it's ui plus 1 and ui plus 2. It's all the forward points from ui for the first derivative. Ta-da! Now we have second derivatives. So let's get a second order. I'm not going to go too far with this. I'm almost done, actually. So let's do a second order accurate central difference approximation to the second derivative. Second order accurate central difference approximation to the second derivative. So now I want to solve for d squared u dx squared. So once again, you look at all these Taylor series that you have, and you look at them and you say, well, how could I combine them, add them, subtract them, multiply by stuff, and so forth, in order to get an expression for the second derivative? Turns out, all you have to do is add these two equations together, 8.5 and 8.7. Those are the Taylor series for xi plus 1 and xi minus 1. Just add them together, and you get this. You'll notice that the first derivative term gets eliminated. So now I can solve for the second derivative. I do that, and I get this. ui plus 1 minus 2 ui plus ui minus 1 over delta x squared. The first term that's truncated is this delta x to the 4 divided by delta x squared, which gives me delta x squared. So it's second order accurate. Second order accurate because of this. Central difference approximation, because I'm approximating at xi and I have a point to the right and a point to the left. So it's a central difference approximation to the second derivative, because this is an approximation for the second derivative. Huh, well, that was fun. And you can just keep going and going and going with these ad nauseum. Or more likely, you'll look them up in a book or on Wikipedia. and they're all there. All right, so a couple comments about these, and then we'll be done. I think we're about out of time. So you'll notice when you compare these first order and second order accurate forward difference approximations, as I said, in order to up the order, you need to include more points. And that makes sense. If you want to increase the order of the approximation, you need more stuff in the approximation. You need to include more points in order to accomplish that. So that makes intuitive sense, and that comes from the Taylor series. And now what you'll notice, and you probably have already noticed this, as you get to more complicated situations in terms of getting these approximations, what if I wanted an approximation at xi that had 1 point on the left and 3 points on the left? So it's not even a forward or backward difference. I want 1 point on the left, 3 points on the right. Well, you can do that. You just have to figure out how to combine the Taylor series approximations in just the right way to accomplish that. But it gets very messy, and we need a better approach. So that's what the second point is talking about. So another approach is to first decide on what's the finite difference stencil. And what that means is decide on the points I want to use. So for like the second derivative, I had a central difference. And so that involved 3 points, xi minus 1, xi, and xi plus 1. Let me just say from the start, I want to use those 3 points. And then approach the problem by asking the question, if I have those 3 points, what is the best finite difference approximation in terms of the smallest truncation error that involves those 3 points for the approximation that I want? It's a very different approach. It's all grayed out here. You're not responsible for this. It's there if you're interested in it to see how it works. I just want you to know that there is another technique. So when it gets kind of complicated, figuring out how to combine these Taylor series together to get these various approximations, there is another way to do it. I just want you to be aware that that is the case, but you're not responsible for it. All right, so we'll stop there. And then on, what is today, Thursday, on Tuesday, we'll pick up with how we apply this to boundary value problems. And then we'll look later on initial value problems. The hardest part of all of this is what we just covered. It's the Taylor series. That's the hardest part. Everything else is relatively straightforward from here on out. Okay, let's see what profound things our colleagues have said in the chat. Imagine an India, oh, cricket. I tried really hard when I was in England to learn to appreciate cricket. And I just couldn't. Maybe you can say I didn't give it enough time, didn't give it enough of a chance. I just could not get into a sporting event that lasts multiple days. That just seemed a little much for my American sensibilities. I think he bet there would be a streaker and decided, yeah, okay. Yeah, that's about as exciting as American sports gets when the fans start streaking on the field. No one's getting stabbed, no one's getting killed, which is good, but just don't need to see that. Have you noticed when that happens, the cameras always go away? Do you know why they do that? Well, right. So the ad people and viewers will complain, especially if it's during a Super Bowl with lots of young kids watching. But more importantly, to the TV people, they don't want to seem to appear to promote these activities because then it would just invite more of it. So they always pan away and they show the crowd. You're like, why am I looking at the crowd? And why is the crowd going, ew? Well, it's because someone's running on the field with, well, maybe no clothes, or maybe they're wearing who knows what. Anyway, some appropriate attire. All right, see you guys on Tuesday. I'll get those exams done. I'll let you know when they're done, and you can take it from there. Yep. Yep.